Kia ora, and here's a question from the 2012 Scholarship Calculus paper. This is one that we haven't done in class yet, and it's a kind of a conics problem, but it's kind of not much of a conics problem once we've done the first bit. So it goes like this. We've got a family of ellipses given by this, and all you really need to know is what an ellipse looks like. So an ellipse looks like this. B and C and R are constants. We're asked to find an expression for dy by dx, so the gradient anywhere on one of those ellipses. Hence, find an equation in this form for the family of curves that always intersects these ellipses at right angles. So the first thing we're going to do is find dy by dx here, and that should be fairly obvious if you're watching this, that we're going to do that using implicit differentiation. You could do it the long way by making y the subject, but that would be a bit of a waste of time. That's probably only worth 1 mark in the question. And then from there, we've got to do something with not much to get an equation in this form. So the key idea here is that this family of curves is going to intersect at right angles, and that should get you thinking that perpendicular gradients multiply together to give you -1. And that's the big idea in this question. So let's start off by doing the implicit differentiation. We're going to get 2bx plus 2cy dy by dx is equal to 0. And that gives me dy by dx is equal to -2bx over 2cy, which cleans up to -2x, -bx over cy. Right, so that's the gradient on the ellipse, any of those ellipses, but we want to have the gradient that's perpendicular to that. And from there we're going to find a family of curves. So we'll go on to a new slide to do that. Okay, so the ellipse gradient is this one. Dy by dx is equal to -bx over cy. But our gradient, a technical term, our gradient is going to be equal to -1 over that. So it's going to be -1 over -bx over cy. Right? Because perpendicular gradients multiply to give -1. Right? And you need to write something like that down. So the gradient we're working with is going to be cy over bx. So our family of curves is going to be defined by this. The gradient of our family of curves is going to be that. And I think if you see it like that, you spot what to do next, which is that we've got a differential equation, and the only thing we can really do, because we don't know much about d's, is to separate the variables. So doing that, we get 1 over cy dy is equal to 1 over bx dx. And then we integrate both sides with respect to y and with respect to x. So on the left hand side, that integrates to give me 1 over c log y. And on the right hand side, it integrates to give me 1 over b log of x, and I'll call it plus k. You could have little c and big C, but that's a bit mucky. Right, now let's reorganise. So we get the log of y is equal to c over b times the log of x plus my constant of integration. We're getting quite close to the end here, so we're going to go y is equal to e to the power of c over b log of x plus k. Now amazingly, when I looked at the schedule, that actually got 4 marks, but that's a little bit less far than I'd like us to take it, so we're going to do a little bit more cleaning up with this. I'll do that on another slide. So pause the video here and just see how far you can take that to get a really nice family of curves. So we got to here, y is equal to e times c over b log of x. I seem to have lost my absolute value signs. where am I? Plus k, there. I'm happy that I've lost my absolute value sign for y because e to the power of anything is always going to be positive. So I can split this into two bits. I've got e to the power of c over b log of x times e to the power of k, which I'm just going to relabel e to the power of k as just k. So I've got k e to the power of... Now, if I chuck this c over b back into here and make it a power, then I can see a really nice solution coming up. But this is not really nice, this is really messy. So we're just going to erase some of this. Let's see if I can do that. No, I can't. Okay, never mind. No, we will mind because it's just such a mess. Let's just clean this up here. All right, hopefully no proper maths teachers watching. There's k e to the power of c over b log of x. So that's my first step. My second step is to say that that's the same as the log of x to the power of c over b. And since e and the natural log are inverses of each other, that simplifies to give me this: y is equal to k times x to the power of c over b. Okay, so what have we learnt from this? Well, we started off with a problem that looked like a conics one, and we had to do some implicit differentiation again. So hopefully you're seeing just how useful that technique is. If you've got any doubts about how to use it, go and look in Delta or come and ask your maths teacher, but make sure that you've got implicit differentiation down pat. And then the other thing that popped up in here was the idea from level 2 about perpendicular gradients. So we're going way back to some really quite straightforward maths. And then the last thing that came up in here was a differential equation, when we didn't really see that from the wording of the question. Okay, so thanks for watching, and I'll be back with more later on.